again. In this section of our seasonal climate videos, scientist Tammy Janes will be explaining some common approaches to presenting seasonal forecast information and show how these are calculated. Then we're going to talk about how we can assess the accuracy and skill of seasonal forecasts. Some parts of this video are going to get quite technical, but they are important to understand, so it's worth taking your time. In the previous video, we explained how seasonal forecasts are produced using an ensemble approach. Each ensemble member is a forecast for the same season, and the range of different outcomes describes uncertainty in the forecast. Then we also have hindcast ensembles, which use a similar approach with the model run over a 20 to 30 year period in the past to calculate model climatology. As previously mentioned, the Met Office GLOW C5 model produces 42 different forecast ensemble members. And now that's an awful lot of data. Tammy, can you tell us how we process and display all this information?
Yep, of course. So one common method we use is to take the average or the mean of the forecast ensemble members for a particular climate variable such as temperature. This ensemble mean gives us a simple central estimate for the forecast. The difference between particular conditions and long-term climatology is known as an anomaly. And what we're interested in is the difference between the forecast ensemble mean and the model's own long-term climatology as calculated from the hindcasts. This is known as an ensemble mean anomaly and can be calculated at each grid point within a model to produce a map. This forecast shows the ensemble mean anomaly of surface temperatures averaged over June to August from an ensemble forecast issued in May 2019. Here, the output suggests that for this season, much of Africa is forecast to be around average, although parts of Central Africa are forecast to be cooler than average by about 2 to 3 degrees, and parts of South Africa are forecast to be up to 2 to 3 degrees warmer than average. Remember that this is just the average of the forecast ensemble members. Some members can be very different, therefore the spread of possible forecast outcomes is also important to consider. So another way of displaying seasonal forecast information is to compare the distribution of ensemble members to categories representing the long-term climate. For example, we can divide the historical climate data into 3 equal categories or terciles representing above average, near average, and below average conditions.
And then how do you go about calculating these tercile categories for a region?
First, we consider the climatology over the historical period. For producing dynamical seasonal forecasts, we use the model climatology determined by the hindcasts. The process of categorizing the climatology can then be explained using a simple analogy. Here is a group of 15 people, and we want to categorize them by their height. There is variability in the group's height, so one way to help organize this information is to sort them by height order. Now, to group them into terciles, we need to split them into 3 equal groups with 5 people per group. One group includes the shortest 5 people, or the below average tercile. Another includes the tallest 5 people, or the above average tercile. And the remaining people are in the near average tercile. Each tercile category includes 1/3, or about 33% of the total group. We could also split our data in other ways. For example, splitting the group into 5 equal groups known as quintiles. In this analogy, splitting the line into 5 groups gives us 3 people in each, or 20% of the total group. This helps us identify the more extreme heights, such as the very tallest. Splitting the data into quintiles might be especially useful when dealing with seasonal climate data, if we're interested in understanding the probability of more extreme conditions that could be linked to droughts or flooding, for example.
So in this analogy, we're looking at people, splitting them into height order and terciles relating to their height, but of course you can do that with climate data as well.
Yes, so what we can do is imagine that a person's height represents the seasonal total rainfall for a particular year, for example, and we can categorize the rainfall data in the same way. So how about we take a look at an example. Here are 30 years of rainfall totals for East Africa from 1981 to 2010, representing the climate of the region. There is natural year-to-year variability with some wetter years and some drier years. Let's now rank these years from the driest on the left to the wettest on the right. The data can then be easily grouped into terciles. We'll label the 10 driest years as drier than average, the 10 wettest years as wetter than average, and the middle 10 years as near average. This allows us to define rainfall thresholds between each of the tercile categories. When we construct terciles using dynamical model data, we use the same process but with hindcast data, using multiple ensemble members instead of observations. We can also construct a frequency distribution from the data, producing a curve showing the likelihood of a particular amount of rainfall based on our past data. The area under the curve for each tercile is 1/3, or about 33% of the total area, and each tercile category has occurred 1/3 of the years in this period. Now let's imagine we have just generated our forecast by running our dynamical model. Each ensemble member has given us a different seasonal rainfall total for the next season. Using the ensemble output, we can construct a forecast probability distribution and see how many ensemble members fall into each historical tercile category.
So here the forecast distribution is towards the higher rainfall totals.
Yes, so you can see that just over half of the ensemble members forecast rainfall above the historical upper tercile threshold. There are only a few in the lower tercile category, and the remainder are in the middle. So the probabilistic forecast from the ensembles suggests that the next season is 55% likely to experience above average rainfall, 30% likely for near average, and only 15% likely for below average rainfall.
So a 55% chance that this season will be wetter than average. With those kind of numbers, we can be pretty confident that it will be a wet season, right?
Well, not necessarily. We have to remember that the seasonal forecast might be suggesting above normal rainfall is more likely than not, but there's still a 45% chance that rainfall could be within that near average or below average category. So the context for using this information might therefore alter how the forecast should be communicated. As well as terciles, there may be specific fixed trigger values or thresholds that are important for decision makers. The output of seasonal forecasts can be processed to display the probability of those thresholds being exceeded. In our example, let's imagine that seasonal rainfall over a threshold of 300 millimeters may lead to damaging impacts on crops. The forecast shows that there is a 15% chance of reaching that threshold in the next season, which is more likely than average. Before using and trusting the output from a seasonal forecast, it's important to understand how well forecasts have performed in the past. This can be done using the hindcasts to determine the extent of any model bias. Looking back at the flow diagram, this is done by comparing the hindcasts with the observed climatology of the same region and period. For example, here is the model hindcast in black and observations in orange over East Africa in the 30-year period from 1981 to 2010. You can see the model has a wet bias, as it has predicted more rainfall than was observed. The average bias over this period is calculated to be about 1 millimeter per day from all points. We can remove this bias by subtracting 1 millimeter per day, and then the hindcast fits the observations much more closely. Future forecasts can then be adjusted in the same way, accounting for the model's average wet bias. So removing the bias in dynamical models is known as model calibration, and this is done using much more sophisticated statistical techniques.
Okay, now Tammy, in quite a few of these videos we've talked a little bit about the importance of assessing the performance of seasonal forecasts. Can you tell us a little bit about how that's done?
So that's right. When considering seasonal forecast output, it's important to assess the performance or skill of that forecast in the past. Forecast skill can vary over space and time, and there are many different ways to define and measure this skill. Ideally, all methods require data sets over long periods, typically 20 or 30 years. One common method we use to assess forecast skill is the relative operating characteristic, or the ROC diagram. And this compares the number of forecast hits against the number of false alarms for a particular event, such as above normal rainfall. Let's say that advisories are sent to farmers if the forecast probability of poor rains, for example the probability of being in the drier than normal tercile, is 40% or more. If an advisory is issued and then the poor rains occur, it's a hit. Otherwise, it's a false alarm. By looking at many cases, a hit rate and a false alarm rate for the advisory statements can be calculated to measure forecast performance. Plotting the hit and false alarm rates against one another is called a ROC curve. In this example, when the probability of poor rains, or the lower tercile represented by the red line, is 40%, the hit rate is 50%, and the false alarm rate is 24%. This can be repeated for other probability thresholds, forming a curve. For a skillful forecast, hit rates must exceed false alarm rates. So when the curve is closer to the top left corner, this indicates a more skillful forecast model. The total area under the curve is a summary statistic of overall performance called the ROC score. In this example, the ROC score is 0.69. ROC scores can also be displayed as maps by calculating these scores at each grid point in the model. The skill can vary considerably depending on season and location. This map shows the ROC scores for the Glossy 5 system for the above-average rainfall tercile category in the June to August season. In general, you can see that for this season, the model performs better over places in the tropics. Before communicating or using a seasonal forecast, it's very important to understand its skill, but we know it can be confusing. There are many other skills available, such as reliability diagrams and Breyer skill score. For more information on ROC scores and reliability diagrams, you can look at the user guidance provided on the Met Office website.
Thanks very much, Tammy. So in this video, we've discussed some common approaches to displaying forecast data, including the ensemble mean anomaly, which is the difference between the forecast ensemble mean and the model climate. Another approach is to categorize them based on the historic climate. The most commonly used categories are terciles, 3 groups, and quintiles, 5 groups. We've discussed the importance of hindcasts, which allow us to identify model bias and forecast skill for your area and season of interest. In our next video, we will explain some of the uses of seasonal forecasts and give some examples of how they're being used in real life.